Hello, Algebra 2. So from here on out, we're going to be focusing on trigonometric identities. An identity is basically two ways to look at the same thing. So you can use identities to rewrite a trig equation to make it easier to solve, or in calculus sometimes we need to rewrite the trig equation so we can do an operation. It wouldn't make much sense for me to say right now what it is you would do with that, but being able to transform an identity, a trig equation or expression, into another simpler expression is pretty important as you move forward in math. And for the rest of this chapter, that's what we're going to be focusing on. So you will have these, you'll want to keep these as a reference for yourself as we move forward. So the first set we're going to look at are reciprocal identities. So we've already seen, remember that cosecant is the reciprocal of sine. So remember that also from before, that meant it works both ways when you have a reciprocal function. Sine is the same thing as 1 over cosecant theta. Something else to also notice is if I cross multiply, sine theta times cosecant theta equals 1. So when you are simplifying, if you can get a product of two reciprocals, it's really nice. Secant, we know, is the reciprocal of cosine, which again, that also means that cosine is the reciprocal of your secant, and also if you get their product, so if I cross multiplied, it would also equal 1. And our last reciprocal was cotangent and tangent. So again, that also meant it works both ways. Tangent equals 1 over cotangent. And again, if we cross multiply, it's really nice. If you see two reciprocals being multiplied together, the product equals 1, which is a nice simplification. The next property or identity that we want to look at, and you've seen this before because remember, tangent is opposite over adjacent. Sine represents the opposite in the unit circle. Cosine is the adjacent. So tangent is that reciprocal. And cotangent, since it's the reciprocal of tangent, is then cosine over sine. All right, and one of the reasons why these are important is that when you are doing your trig identity, some people feel most comfortable putting everything in terms of sine and cosine, so that's a quick way to do that. All right, so let's see how this works. Simplifying. Simplify means you get it down to as simple a term as you can. Usually you're reducing it to one term if possible. All right, and it's not a ratio, but a simplified term. So I have sine x, cotangent x, secant x. So what I'm going to do, sine x can't really be simplified. It is what it is. Cotangent, I'm going to substitute cotangent with its reciprocal property, cosine x over sine x. This is how you do identities. It's basically substitution. I'm then going to substitute secant with 1 over cosine x. And now we look back and see, can I simplify? Well, this will cancel to 1, and this will cancel to 1. So this whole phrase here cancels to 1. And that's kind of cool, because 1 is way easier to deal with than sine x times cotangent x times secant x. That is what we do when we simplify. It's basically substitution with another version. Now the last identity here we're going to talk about in this first section are the Pythagorean. These are the most used identities. And you might have already seen these last year. We know that if you have a right triangle, we know that if this is the x and this is the y, remember if this is the unit circle, so the hypotenuse is 1, we know that x squared plus y squared would equal 1. Well, in our unit circle, we also saw that x is the same thing as cosine theta, and y is the same thing as sine theta. So you get the identity that cosine squared plus sine squared is 1. And that is really powerful. That is the one I would say is the most important to remember. Then what I have shown here is it's not always going to come to you in that form. I can isolate. There's 3 terms here: cosine squared, sine squared, and 1. I can isolate each term and come up with a different version of the same identity. So if I isolate cosine squared, notice I get 1 minus sine squared. I can isolate sine squared, and then I get 1 minus cosine squared. So it's helpful to recognize these other versions. Now the next 2 identities, Pythagorean identities, can be quickly derived. The first one we're going to derive by dividing all the terms by cosine squared x. So if I divide everything here by cosine squared x, and then use my reciprocal and ratio properties, this becomes cosine squared over cosine squared is 1. Sine over cosine is tangent, so this becomes tangent squared. 1 over cosine is secant, so that becomes secant squared. And that is your second identity here. 1 plus tangent squared equals secant squared. And again, so it's really easy to derive them. You don't have to memorize them. So this one comes from dividing all the terms in your original Pythagorean by cosine squared. And again, what I've done here is isolate each different term. So in the first one, secant squared is isolated. In the second one, isolating 1 is equivalent to secant squared minus tan squared, or I can isolate tangent squared and it becomes secant squared minus 1. You never know which version you might want, so it's helpful to recognize all of them. Then this next one, since the last one I divided by cosine squared, now I'm going to divide everything by sine squared. So going through every single term, we divide by sine squared, sine squared, sine squared, and the result is going to be cosine over sine. Looking up here at your cotangent, that becomes cotangent squared x, plus sine squared over sine squared is 1. 1 over sine is your cosecant, so this becomes cosecant squared. And that is our third Pythagorean identity, where the cosecant squared is isolated. But notice if I isolate cotangent squared, I get cosecant squared minus 1, or I can isolate the 1, so it's cosecant squared minus cotangent squared. Okay, so let's take a look at how you can use these in an identity. Now, doing identities and simplifying trig identities, kind of like geometric proofs, and I know that's a dirty word, but they're a little bit easier. You don't have to justify each step, but you do want to do each new step on a new row. And there are certain strategies I can recommend, but there's really no rote one way to do these. So the first strategy in this problem right here, well, the strategy we saw in the last one was we turned everything into sine and cosine and then simplified. The strategy here is you look for a common factor. Always look for a common factor. So I notice cosine is common to both terms. So when I factor it out, I have a placeholder of 1 minus sine squared theta. Okay, well that's not very simple yet, but then we look up at our trig identities. Anytime you see a 1 and something squared, come back and look at this box and see if you can find an identity that would go with that. Notice up here we have that 1 minus sine squared is the same thing as cosine squared. So I'm going to substitute this right here with cosine squared theta. So my final answer is going to be cosine cubed. And that's it, you're done. So usually you're getting down to just one term, and the strategy was here that we used was factor out a GCF, greatest common factor. That is a very common strategy. All right, let's continue and get a few more identities. And again, you're not having to memorize these. Our goal is for you to know how to use them, all right? So we're going to first look at the co-function. I've already kind of talked to you about the co-function property. Co, just like in geometry, means complementary, two angles that add up to 90 degrees. That means the acute angles are a difference of 90 degrees. That's where these properties come from. So you have that cosine is equivalent to sine pi over 2 minus theta. You have that sine is equivalent to cosine pi over 2 minus theta, because that's sine, cosine. They're complementary to each other. We have here tangent pi over 2 minus theta is equivalent to the cotangent. Hopefully you remember that from our graphs. We tried to emphasize that the graphs are just a translation of 90 degrees. And here's that property. And again, you could substitute instead of pi over 2, there could be a 90 degree here. It won't always be radians. It would be the same identity in each case. All right, so these are used, mainly you're going from the more complex to the simple. So if you ever see sine pi over 2 minus theta, you can substitute in cosine theta. Then we have the negative angle identities, and it looks like I must have redone these a little bit so it went on to the next page. Let me show you the justification for these. Draw a little unit circle here. So this first one says that if I have sine of a negative angle, so remember we have all students take calculus. That means all of your trig is positive in the first quadrant. Sine and cosecant are positive in the second quadrant because they represent the y value. Tangent and cotangent, its reciprocal, are positive because a negative over a negative is a positive. Everyone else is negative. And in the fourth quadrant, only cosine and its reciprocal secant is positive. Okay, so sine negative theta, that would be down here. Well, sine of a negative theta in this fourth quadrant, sine would be negative. So the sine of a negative angle is the same as the opposite of the same. That may sound crazy, but the way this works is, so if I gave you sine negative 30 degrees, that would equal the opposite of sine 30. That's what that means. It's considered a simplified form if you don't have a negative in front of your angle. So you could pull the negative out in front. Cosine, on the other hand, if I take a negative angle down here, remember now cosine is positive in the negative quadrant. So you're allowed to, if you have cosine of a negative angle, you're allowed to just drop that negative. So for instance, the cosine of negative 30 degrees, and you can even test this on your calculator, is the same as the cosine of just 30 degrees. It doesn't matter. And this one's going to be really helpful when you're solving equations, to be able to substitute these. Tangent is also, this one is not correct because this should have a negative in front. Sorry for that. tangent, I should do it in a different color, right? So here's tangent. Tangent of a negative angle, tangent is negative down here. So tangent of a negative angle is going to be the opposite of tangent theta. All right, we're going to do an example on the next page. Okay, so we have here, given that sine theta equals 4/5 and theta is between pi over 2. So this information right here is telling me where to draw my triangle, which quadrant. So remember, pi over 2 is like 90 degrees, pi is 180. So the triangle, again, it's going to be one of your bow ties, so they're always coming out of the origin perpendicular to the x-axis. So this is where we're going to draw this. It tells us the sine of that angle is 4/5. So remember, sine is opposite over hypotenuse. So this side will be 4, this side will be 5. We would do Pythagorean theorem to figure out what this last side is. Now this is going to be a little tricky because we do know, hopefully you already realize, I'm going to put an x here. But I want you to realize this will end up having to be a negative x because in this quadrant, you're coming back. But let's just first find x. X squared plus 4 squared equals 5 squared. That means that 25 minus 16 is 9. We have to take the square root, so this side will be a -3. Pythagorean will only give you the positive value, so you need to know that in the second quadrant, the x value is negative. So we have a -3, 4, and 5 for the sides of our triangle. So this told me how to label my triangle. The theta gate told me which quadrant because that helped you know whether x or y is positive or negative. Your hypotenuse is 100% of the time positive. So now I can read off the cosine of theta is going to be the adjacent over the hypotenuse. That's where that negative comes in, so it's important to have the right sign. And the tangent of theta is the opposite over the adjacent. So notice both of these need that -3. And again, here is your sign chart over here. Just to remind you, this is where x and y are positive and negative. All right, now we are going to start getting into doing some of our simplifying trig. So why is my eraser not working? That's really weird. Just give me an eraser. I don't know why it's not erasing. There we go. Awesome. All right, let's do this. I love these. I'm sorry. It's just something. All right. So again, what you're doing, you're going to want to be able to look back at the first page. Simplifying is really basically substitution until we can get down to a much simpler form. And you do each substitution, each transformation really on a new line. So each transformation, which means like each substitution on a new line. All right, so my next line here is going to be, I'm going to substitute tangent pi over 2 minus theta. There's your co-function property. I'm going to substitute with that cotangent theta times sine theta. And it's like, okay, that's nice. I don't really see anything to simplify yet. So now I'm going to rewrite cotangent in terms of cosine and sine. Cotangent, remember, is cosine theta over sine theta. So we're just substituting each time times sine theta. This is like over 1. Now I see, I can cancel these out, and the whole thing simplifies to just cosine theta. So when you get down to just one simple trig, you're done. And that was it. All right, so that was using our cofunction property. Now let's come over here, secant theta, tangent squared theta plus secant theta. So here's that property I said, or strategy that you always want to look for a GCF. So the first thing I'm going to do is factor out secant theta. that leaves me with tangent squared theta plus 1. Anytime you see something squared and a 1, it's not necessarily your Pythagorean identity, but you do want to go back and check. Sometimes it is. And in this case, this can be substituted. So we still have secant theta, but tangent squared theta plus 1, if you look at your Pythagorean identities, is equivalent to secant squared theta. And the whole thing now boils down to secant cubed theta. I have 3 of them. And you're done. All right, so it's really about knowing what the identities are, and again, so keep them handy as a reference. Now, these are simplifying, which in some cases is harder because you don't know where you're going. You're just simplifying, but the idea is you usually get it down to either one term and that's it. If you actually do verifying an identity, that means you are going to only work on one side, usually the more complex side, and you keep going until you get what was on the other side. So you already know what the answer is, you're just showing how to get to that answer. That's the idea behind these. So we got 4 of them here. And I'm just gonna have to tell you, trig identities are one of my favorite things. They're like little puzzles, but it's the same thing as the simplifying. You're just basically substituting. We will get some more complex strategies as we move along, but in this section, it's really just using those identities we just introduced. So here I've got tangent theta, cosecant theta, cosine theta equals 1. So I'm not going to touch the 1. I'm only going to work on one side until from this one side I get down to 1. So let's start. Tangent theta, I'm going to turn everything into sine and cosine. So tangent theta is sine theta over cosine theta. Cosecant theta is 1 over sine theta. And cosine is just cosine. There's not really much you can do to it, but I'll put it over 1 just to emphasize what's happening. Now I look at this and I notice, this sine would cancel with that sine, this cosine would cancel with this cosine, and that all would cancel down to 1. And notice that is on the other side, so I'm done. There's your first trig identity. Let's try another one. So here I already have sine squared x. There's not much I can do with that right off the bat. So I'm just going to write sine squared x. What can I do with 1 plus cotangent x? Well, I see a 1. I see something squared. I look at my identities for the Pythagorean, and I notice that this is the same thing as cosecant squared x. All right. Well, at this point, you can either notice that you're multiplying 2 reciprocals together and call it 1, but if you don't see that, it's totally okay. Let's take this one step further. Cosecant squared is the same thing as 1 over sine squared, and now we can see that the 2 of those would cancel and give me 1, which is what we have on the other side. And there we've done our second identity. Okay, so now they're going to get progressively a little more difficult. So let's see what we can do here. I see a sine over a cosecant plus cosine over secant. So I see a ratio of the reciprocal properties. So this one, sine, I'm going to spell this out. You don't have to do this first step here, but I just want to do it to emphasize that what I have here is sine x times 1 over cosecant x plus cosine x times 1 over secant x. I just want to emphasize that. You don't actually have to write that step out. So what can I do with this? Well, sine you can't really do anything with. It is about as simple as it's going to get. 1 over cosecant, though, that is your reciprocal. That is the same thing as sine. And then cosine, again, not much you can do with that, but 1 over secant is the reciprocal of cosine, so I can write it as just cosine. And now, notice you have sine squared x plus cosine squared x. So I have something squared plus something squared. We look at our Pythagorean identities and see, oh, together that equals 1, which is what we were after, and we're done. I hope this is going okay. All right, now let's talk some strategy here. There's, like I said, there's more than one way to do these. When I don't see anything I can really simplify in the parenthesis, and I am going to work on the left-hand side here. I am going to work on this side because it's more complex, but I know that I want this now not to simplify to 1, but I want it all to simplify to cosecant x. So what I'm going to do, because I don't see a Pythagorean identity in that parenthesis, there's nothing squared, there's no 1, I'm going to just distribute. So the first step I'm going to do is I have cosine x times tangent x plus cosine x times cotangent x. So all I did was distribute cosine to both terms. And I haven't even changed anything, I just distributed. Now I'm going to rewrite everything in terms of cosine and sine. So cosine x doesn't change. Tangent becomes sine x over cosine x. Cosine does not change because it's as simple as it can get, but cotangent, remember, is cosine x over sine x. All right. This is a good one to look at. What do we have here? I have cosine times, and I'm gonna, this is all over 1, so I can just extend this as a fraction. I'm trying to add 2 fractions that have different denominators. And so what I want to do is create the same denominator. But I'm sorry, I got ahead of myself. Over here, notice that cosine cancels. So what I really have, just to spell it out, is I have sine x plus cosine squared x over sine x. So I'm trying to add 2 fractions that do not have the same denominator. So I'm going to multiply top and bottom here by sine. So that means this one becomes squared, and I have a sine x here. Now I have, so this is a common strategy when you have 2 fractions and you need to make it into one term, because that's what we're trying to do, is get one term. You will always have to get a common denominator. So now that I have a common denominator, sine squared plus cosine squared, notice that's going to be a very common identity. That's going to equal 1 over my common denominator of sine x. And as I said before, usually simplifying, well, first of all, this is an identity where we know what we want. So if I was just simplifying, I still wouldn't stop there, because you want to always give just the term, not the reciprocal of a term. So the reciprocal of sine is cosecant x, which is what we're after, because that's what we're trying to show it all equals. All right? So have fun with these. I really like these. They're just kind of little puzzles, but they're all based on using those identities.